Okay, so welcome to our first little section on measure theory, which is from chapter 3 in this module. And we're going to start with section 3.1 on the extended real line, which is your big chance to learn how to add and multiply by infinity. All the things that you were told, never do this or you'll be marked down because it's illegal and incorrect and you mustn't do it. You're going to have the pleasure of being allowed to work with infinity correctly. Even better, the best thing that comes out of all this is that you're going to discover that n tends to infinity as n tends to infinity, which is a truly remarkable fact that you would never have guessed. Now, we have limited time in this module. We won't be able to go through all the details, but I did do some more details when I taught this module to the third years, when I taught measuring integration to the third years. If you look at my, this is a short link to a much longer link, which is on my blog, which then links to various places where you can get the audio and no video, unfortunately, yet, but you can get audio podcasts from my lectures from 2006 and 2007 on measuring integration, and all the annotated slides and everything. So there's plenty of information there, much more than you need to know. You can't possibly go away and learn the whole of a 15 credit, a fairly difficult 15 credit level 3 module in the middle of a 20 credit level 4 module. Okay, but what there is there is some additional background material that you might find helpful if there's something here where you'd like a few additional explanations. And the warning on there, I did used to call sigma algebras sigma fields. They're all, there's lots of different names for the same thing, but I found that sigma algebra is more common in the literature. So we'll call them sigma algebras this year, like I did in functional analysis last year. So we're on to section 3.1 on the extended real line. What is the extended real line? It's the closed interval from minus infinity up to infinity inclusive, which means, roughly speaking, you take the real numbers and you need to find two more things to throw in. Now, I don't care what those things really are. We're going to call them plus infinity and minus infinity. Or, I'll often, if I say plus infinity, it's the same as infinity in this module. And then there's minus infinity. And that's just notational. It just means two more things that weren't in the real line and which we're going to think of as living at either end. But it doesn't actually matter what those two things are. As long as you manage to find a slightly bigger set, which has got the real numbers in and two more points. And now we're going to make some just formal definitions so that we can define a structure on it. Just like if you've got any set, you can find some suitable algebraic structure or anything that you can put on it. That's what we're going to do now. Real line, two more points, and now we're going to define some structures on it, as a result of which plus or minus infinity are going to behave the way you would expect them to, but we're going to have formalized it. So our first task is to say, as I said, that the extended real line is the ordinary real line with two new points, whatever they are. Then we have to decide what we're going to do with these two new points. And what we have to do is extend our old notions. So we already have a total order on the real line, the usual order. And we just want to extend that so that minus infinity and plus infinity are included as well. And that's obvious because just by the notation, we know what we wanted to do with them. We say minus infinity is at the left-hand end, plus infinity is at the right-hand end, and the real numbers live in between. So we simply make the obvious definition in order to extend less than or equal. So this is a new less than or equals, extending the old less than or equals, but we'll still use the same notation. That way we won't forget that it's the same as it used to be if you're actually working with real numbers. So everything is less than or equal to plus infinity, which is the same as infinity, and everything is greater to minus infinity. All sorts of really nice things happen that I won't spend too much time on, like, you know, when you wanted to have least upper bounds and greatest lower bounds, you always had to say if you have a non-empty set which is bounded above or bounded below, then you can take a supremum in the real line and so on. There's no problems like that. In the extended real line, it's great. You just say every subset of the extended real line has got a supremum, a least upper bound, and has got an infimum, the greatest lower bound. Because essentially either you get the old one that you used to get from the real line, or you end up with one of the plus or minus infinities. With a really weird special case of the empty set, because the supremum of the empty set, the least upper bound of the empty set is minus infinity, and the greatest lower bound of the empty set is plus infinity. This is the only set where the greatest lower bound is strictly less than the least upper bound. More details on that if you go back to the measured integration notes. We won't need to deal with that. The other thing that we did in the measured integration notes that we're not going to need in this module is some very useful things I dealt with there called the limit from the lim sup, something you can apply to any sequence. I won't go into that in this module, but it is very useful if you want to do any further analysis. So if you do want to go on and do analysis to any greater depth, I would suggest that you find out about some of the stuff in measured integration that we don't cover in this module. Okay, so now of course you can define various kinds of intervals. The old real line is what it was before, the open interval between minus infinity and infinity. The extended real line, as I've already said, is a closed interval between minus infinity and infinity inclusive. But most of the time in this module, we're going to work with the non-negative extended real numbers, which are extended real numbers between 0 and infinity inclusive. So most of the time, we won't be fussed about minus infinity, and most of the time, we won't be fussed about the negative real numbers when we're doing the measure theory. Just occasionally, I might mention something about them. Okay? Any questions about the extended real line or what we've said so far? All it is so far is a set, and we're gradually putting some abstract structure on it so that we know how to manipulate it. So far we've just got an order. Now we want a notion of convergence. Now I did this in much greater detail when I taught measured integration, but I'll tell you what you need to know in this module. Actually, well, first of all, I'll give you a way of thinking about it. It's not the only way of thinking about it. But the idea is that in some sense, we're going to treat the closed interval minus infinity infinity rather like the closed interval minus 1, 1. In other words, I'm going to show you how we could put a metric on this set, which actually will make it isometric to that. And that will give us the notion of convergence, with respect to which it will actually be a compact metric space. It obviously won't extend the usual metric from the real line, but it will extend the usual topology. So what do you have to do? First of all, we start with a homeomorphism from the real numbers to minus 1, 1. Now there's a lot of these around. Here's one of them. And I don't really care which one you use, but I would like you to use an order-preserving one. You could flip the order if you want. That would just make everything a little bit strange. So I prefer to use an order-preserving homeomorphism like this one. So the one I'm suggesting here, f of x is x over 1 plus mod x. And if x is a real number, then it'll have a modulus. 1 plus mod x will be slightly bigger than the modulus of x. When you divide them, you'll get a real number whose modulus is strictly less than 1. But you can get as close to 1 as you like. So a little bit of thought will tell you that this is doing what it ought to, and taking R to the open interval minus 1, 1. Now, I'm leaving it to you as a little exercise to think to find the formula for the inverse map, to make sure it really is 1 to 1. You can check the order preserving as well. And there's a homeomorphism. Well, once you've found the formula for the inverse map, you just have to observe that that's continuous as well. This one's obviously continuous. You can find a formula for the inverse map, which is also continuous. Then you'll know it's a bijection. The order preserving is quite easy, and so on. I say any other map with the same properties would do. Anybody else know another one? Who can think of something trigonometric that might? The first thing you think of might do pi by 2, minus pi by 2 and pi by 2 instead, so you'll have to scale it a bit. Any suggestions? Ah, excellent. Okay, so arctan does r goes to minus pi by 2, pi by 2. That's a homeomorphism. So you could use f of x equals 2 over pi, which does your dividing by pi by 2, arctan of x. And that would do just as well. And that's order preserving homeomorphism from the real line to minus 1, 1. Actually, it doesn't even matter. It doesn't really have to go to minus 1, 1. Any open interval would have done anyway for the rest of the argument. You just have to move things around a bit. But I don't really care. So you've done one of these. And now, of course, your function f was defined on R, and it was order preserving, and it's missing the endpoints. So you just take the endpoints to the endpoints. So you extend your function by saying, we'll take our left-hand endpoint to our missing left-hand endpoint, and our right-hand endpoint to our missing right-hand endpoint, and you end up with a bijection. And since we've got no topology yet on the real line, so we've now got a bijection, an order-preserving bijection from the extended real line to minus 1, 1, which behaves properly on the real line, but which, so far it's just a function on the whole thing. But now you can pull back the metric. Here's the pullback metric. I mentioned this before. You did it in G13 MTS probably. If you didn't, then this is how you pull back a metric. My distance in R bar, and I've told you which function f I'm using, but if you want to use your function, it'll be just as good. It won't change anything else I'm going to say, so it doesn't matter. You look at the modulus, usual modulus in R of the difference between f of x and f of y. So that's the usual distance in R, or the usual distance in minus 1, 1, which is the usual distance in R. And now you've got a metric space isometric to minus 1, 1, which makes it a compact metric space. And of course, because of the way we set it up, the real line embeds into it as a sensible subset with its usual topology. So this extends the correct topology from the real line to give you a topology and a metric on, it doesn't extend the usual metric, but it does extend the usual topology. And you've now got a metric and a topology on minus 1, 1. And now you've got a notion of convergence, and that's how you define your convergent sequences. And I'll say a bit more about this next time. But if you've got a sequence in R converging in R with the usual metric, it still converges the way it ought to in the extended real line. All that's happened is we've got some new convergent sequences converging to plus or minus infinity. And I will say a little bit more about that because we'd like to see if you can think for yourself of a definition not involving f that explains what it means for a sequence to converge to plus infinity or to minus infinity. Something with some quantifiers in, like for all positive real numbers m, something happens, and try and eliminate that distance and that function that I mentioned before. So just try and get hold of what does it mean for a sequence to converge to infinity in the extended real line. And you should find out it's rather like the old notion you had of diverging to infinity. Except that nowadays, in this module, they're going to converge to infinity instead, which is good. Okay, I'm going to stop there for today. We'll finish this off next time, and then we'll move on to see things like addition and multiplication in the extended real line.